Good day, everyone. My name is Mohamed Firdaus bin Jamaludin, and today I will be presenting about my final year project, which is titled 3D MRI Reconstruction.
Okay, a brief description about my project. What it is actually. So, my project is creating a desktop application that converts 2D MRI bone scans into an interactive 3D models using advanced image processing and also 3D reconstruction algorithms. Some of the tools that have been used are OpenGL, Qt, OpenCV, and also Marching Cube algorithm. So the main thing that it does is actually generates 3D models from MRI slices. Some of the features it offers are like load MRI images, images preview, apply image processing, render 3D model, model interactivity such as rotation, zoom, panning, and also dynamic threshold control. And last but not least is export to 3D printable formats, which is STL. So why does my project matters? It matters because it gives a medical impact such as improving the diagnostic accuracy for bone tumors, fractures, and also implants. It also gives an educational value by providing an interactive 3D models for anatomy training. And it also offers as a technical achievement by bridging the gaps in MRI based 3D modeling. Okay, let's start by addressing a critical challenge in medical imaging, which is the limitation of 2D MRI scans. So, what's wrong with 2D images? So, the first issue is hard to see details. These scans can often appear blurry or pixelated, like a low resolution photo. Important structures such as bones and implants can get lost in noise or shadows, making it difficult for clinicians to identify key features. The second issue is missing the big picture. 2D slices are like reading a single page of a book. You might grasp part of the story, but you miss the full context. For doctors, this means struggling to visualize 3D anatomy, whether it's a tumor shape or the extent of a fracture, from flat, fragmented images. Here we see a striking comparison, which on the left you can see a 2D TOF MR angiography, and on the right is its 3D counterpart. The disadvantages of 2D MR angiography is that it has limited detail. Thick non-isotropic voxel creates stair-step artifacts, like viewing a smooth curve as jagged edges. This obscures fine anatomical features. The second disadvantage is motion vulnerability. Each 2D slice is acquired separately, so if the patient moves slightly, slices may be misaligned. The 3D counterpart overcome these challenges by having a more superior resolution. Isotropic voxel capture equal detail in all directions, like a high-definition sculpture instead of stacked paper cutouts. It also have a comprehensive coverage, so a single 3D acquisition captures an entire volumes with no gaps or misregistration. So why does this limitation matters? Now let's talk about the real world impact of these limitations. One of the impact is misdiagnosis risk. Ambiguous scans can lead to incorrect treatment plans, delaying recovery or worsening outcomes. Another impact is surgical challenges. Imagine assembling furniture without instructions. That's what surgeons face when planning procedures with incomplete 3D information, which increase the complexity and also the risk. Next, I will be explaining about the three objectives of my project. So, the first objective is to develop a desktop application to combine MRI images and generate 3D object model. The second objective is to apply image processing techniques to extract features and also generates 3D vertices and surfaces. The last objective is to include interactive elements for viewing the 3D model and includes generating STL data for 3D printing compatibility. So, for the proposed solution is a one-click 3D reconstruction application which transforms 2D medical scans into precise interactive 3D models. So, how it works starts by selecting your 2D MRI or CT scan files. So, the system actually supports multiple formats such as BMP, JPG, PNG, and also DCM. The next thing is 3D reconstruction. Behind the scenes, advanced algorithms spring into action. The first thing is advanced image processing, which reduce the noise and also do the edge enhancement to clean up the data. Next is marching cube. This classic algorithm converts voxel data into a smooth high fidelity 3D mesh. Furthermore, we have interact and export. Here you can rotate, zoom, and also explore the model in real time using OpenGL for fluid visuals. And also the user can export to STL with one click, which is ready for 3D printing, surgical planning, or also patient education.
Okay, let me walk you through the overall architecture of my 3D MRI reconstruction system as represented in this module diagram. At the core of the system is the main objective, 3D MRI reconstruction. This is the central process that integrates various functional modules to transform 2D MRI scans into a usable and interactive 3D model. We begin on the left with MRI data segmentation. This module handles two key tasks. First, it loads the source images, typically a stack of 2D MRI slices. Then it proceeds with image processing, which includes enhancing image quality and isolating the relevant anatomical structures for further processing. Next, the data move into the 3D reconstruction algorithm module. Here we perform volume conversion where the 2D slices are compiled into a volumetric dataset. This dataset is then passed through the marching cubes algorithm, which converts the volume into a polygonal mesh representing the 3D shape. Following reconstruction, the output is fed into the mesh rendering module. This rendering engine visualizes the 3D model in real time. Additionally, optimization techniques are applied to improve rendering performance and mesh quality. Moving forward, we have the interactive features module. This allows users to directly interact with the 3D model using user model controls. It also includes dynamic threshold control, enabling real-time adjustment of segmentation threshold to refine the model interactively. Finally, once the model is ready, we reach the Export 3D Printing Format module. This module supports STL export, allowing the 3D model to be saved in a format suitable for 3D printing. So in summary, this diagram shows a complete workflow from raw MRI images to an interactive optimized 3D model that can be printed, streamlining both visualization and practical application in medical and research fields.
Next, I'll be showing you a video of the feedback gained from a real end user, which is Dr. Khairul Anwar, about the impact of my application.
Yang bagus ni tentang 3D image ni adalah kita boleh lihat daripada aspek banyak angle in term of clinical application lah, sebab currently for imaging of the CT scan ke MRI ke, most of them dalam 2D images. So jadi when kita boleh create from 2D to 3D, dia akan banyak lah function dan gunanya. Dan satu lagi saya tengok dia punya Firdaus ni punya apa ni, punya orang kata tab kan simple je, macam open dataset, generate 3D, load mesh dan export STL, itu very simple and friendly user. That's very important lah, sebab kalau orang doctors, dia orang not orang kata IT savvy lah, to be honest. Okay, it's easy to educate the patient lah. Okay, sebab kadang-kadang bila kita pergi consultation, bila doktor explain tu, kadang-kadang kita tak boleh nak cope dengan those explanation. Tetapi dengan ada 3D image ni, patient sendiri boleh tengok dia punya dekat mana kedudukan kanser dia, ataupun dekat mana dia punya ada isu tentang any bone related disease dan sebagainya. Okay, tapi yang impresif ni tentang projek ni adalah you make it into 3D. Tak banyaklah software yang boleh buat 3D yang simple, melainkan kita boleh tengok directly from the software yang install dengan machine. That's a problem. Bila dia install dengan machine, dari segi accessibility tu kurang lah. So jadi dengan ni lebih mudah lah doktor nak tengok data tu on the spot, and then patient pun boleh review easily the location of the disease lah. Kita boleh tengok dekat mana section pun, dekat mana angle, dekat belakang ke, dekat depan ke, sama ada dia form dekat bawah ke, dan secara tak langsung dia dapat membantulah doctors to give accurate diagnosis. That's very important, accurate diagnosis. Okey, sebab kadang-kadang bila kita buat assumption tu agak susah. Okey, tapi bila dengan adanya all this kind of imaging, so dia akan membantulah doktor untuk buat better treatment process, number one, and number two, accurate diagnosis to the patient.
As you just saw in the video, we received valuable feedback from Dr. Cairo Anwar, a medical professional who reviewed the application. His insight highlight not only the usability of the system but also its strong potential in the healthcare market. So let me summarize the key points he shared. First, the multi-angle viewing capability of the 3D model allows doctors to inspect anatomical structures from various perspectives. This makes diagnosis more precise and supports better treatment planning. Secondly, he praised the user-friendly interface since many healthcare workers may not have advanced IT knowledge. Simplicity and ease of use are critical. Our system's intuitive design meets that need effectively. Another strong point is patient education. With our application, doctors can visually explain the patient's condition using the 3D model. This leads to clearer understanding and greater patient engagement during consultation. And last but not least, he emphasized improved accessibility. Previously, 3D MRI models could only be accessed through the MRI machine built-in software. Our solution break that limitation, making 3D visualization available on regular desktop system across various settings. Overall, the feedback confirms that this application doesn't just have technical merit, it also meets real clinical needs and opens up new entrepreneurial opportunities in both the medical and educational fields. Now let's look at the entrepreneurship potential of the 3D MRI reconstruction application. First, the market need is very clear. Currently, most 3D MRI visualization tools are only available on high-end MRI machines using proprietary software. This makes them expensive and inaccessible to smaller clinics or educational institutions. Our solution addresses this gap by offering a low-cost and portable alternative. Our target customers include private clinics and specialist centers that don't have access to advanced imaging tools. It also caters to medical schools and training centers where interactive 3D anatomy model can enhance teaching. Additionally, 3D printing services can use this application for surgical planning and creating physical models. The value proposition lies in its affordability and user-friendliness. It offers essential features like interactive model controls and STL export in a simple interface that doesn't require technical expertise. Plus, since it is a desktop application, it's not tied to any specific machine or location, making it more accessible. In terms of revenue model, we can adopt a freemium approach offering a free version with basic features and a premium version with advanced tools. We can also license the software to hospitals and universities and offer custom services for clinics or device makers that need integration into their systems. Lastly, there's a strong potential for future scalability. We can enhance the system with VR support for immersive surgery planning or enable CUDA-based parallel processing to handle larger datasets faster. It can even be adapted for telemedicine use, allowing remote specialists to interact with patient scans in 3D. So overall, this project is not only technically impactful but also has strong commercial potential in the healthcare and education markets. Next is the system demo. Here you can see the interface of the application. So we have open dataset, generate 3D, reset view, load mesh, and also export STL function. You also have two different tabs, which is image preview and also 3D visualization. So first we open the dataset and we search for the source of our images. After then we can just click the folder and click select folder. So here you can see the images is being loaded. Okay, after the images have been loaded successfully, we can actually preview the images by going to the image preview tab, and here you can see there is 1000 images that have been successfully loaded into the application. You can enlarge the image by double clicking it, and also use the scroll wheel to actually see the image that has been loaded. Next, you can go to the 3D visualization tab and click on the generate 3D. You should see a pop-up notification showing that the 3D is being generated. Here you can see that the 3D model has been successfully rendered. And you can see you can actually interact with the 3D model by zooming in, zooming out, rotation, and also pan the model. Here you can see you can still go to the image preview tab to actually see back the 2D images. Next, I will show you the dynamic threshold control feature. So here you can actually adjust the threshold percentage. So here I'm going to change it to 50%. And then I will click the apply. So it will start to generate the 3D again. Here you can see after the rendering has finished for the new threshold, you can see that less pixels have been generated since the threshold have been increased to 50%. Next, I will show you the export STL feature. So you can click on the export STL and then you can choose the folder where you want to save your STL file. So here, I pick here, and then you can write the file name for your 3D model STL and then click on save. So here it's going to save your file into the folder. After the file have been saved, you can go back to the repository where you saved the file and check back the file to make sure it is correct. Then you can use a third-party 3D viewer such as MeshLab to open back the STL file. So it will load the STL file generated. After the loading has complete, you can actually see that the STL file have been successfully opened in a third-party 3D viewer app and can be used for other usage such as 3D printing. That is all for my final year project presentation. Thank you.